Okay, so now we're going to talk about how we represent chemical reactions on paper. So now that we've kind of introduced, difference between physical and chemical processes, which are things that we've kind of touched on before, but to kind of bring it back into focus, now we're going to be focusing slowly on, not too slowly, not too, hopefully at a reasonable pace, but we'll be looking at chemical equations. And so this is just basically shorthand for chemical reactions. Like, there's all this logic that's packed into a math equation. It's shorthand for all of this logic. 2 plus 2 is 4. Well, that can actually be an incredibly complicated idea, believe it or not. If you take a high enough level of math and you actually start to question things like addition. And we're going to do something similar here, where we're going to have a lot of information packed into very little writing. Which, surprise, that's what chemists like to do. Just like we had the chemical formulas for compounds. Now we're going to talk about chemical equations for reactions. So, here's an example. I just like to start with an example here. So, if we describe a reaction, so coal, which is solid carbon, I'm like totally into this reaction through all these videos this week. Just so you know, you're going to see this one come up a lot. This will be the second time you've seen it already. So it's reacted with oxygen gas, to produce carbon dioxide. Okay? So, that's a long description of a chemical reaction. What does the chemical equation look like? Well, carbon, okay, it's solid, okay. Oxygen gas, well, that's actually O2. We'll talk about that in a second. Gas. They react together and they make carbon dioxide gas. That is my chemical equation. That's it. All of this writing, or I could just do that. So it leverages things like chemical symbols, chemical formulas, shorthand for phases, and then the reaction arrow. This is like the stuff we start with. This is what we end with. Reaction in the middle. So these become this. It's all very straightforward. Very simple to write. A lot faster. So, over here, to the left of the arrow, we have our reactants. We use reactants in a reaction to produce products. So on the right hand side, products. Our reaction arrow will always point left to right. So this is our reaction arrow. Wouldn't be chemistry without some lazy shorthand. RXN is reaction. I'm going to use that one quite a bit. And what else can we talk about here? Oh yeah, we got our phases of matter. You see 2 of them here, S for solid, G for gas. There's 4 total. So if you're dealing with a substance that's in the gas phase, we use a G. L for liquid. S for solid, and there you go. Did he say there were 4? What's the 4th one? AQ, which is aqueous. Okay. And what does aqueous mean? It means dissolved into water. So dissolved into water. Turns out we do a lot of reactions of stuff dissolved into water. It's the easiest, if I need a liquid, it's the most plentiful one. It's not always water, but it happens so much that we came up with a special term for it and a shorthand to go with it, because like I said, we really do a ton of reactions of stuff that's dissolved in water. Okay, O2 gas. So I said oxygen gas. Why isn't it O? Why isn't it just O by itself? Why is oxygen O2? Well, it is a diatomic element. So not all elements are diatomic, but there are a series of elements that can and do form molecules with 2 atoms of themselves. and I've sprinkled them in throughout, but I've never actually explicitly introduced them. And so oxygen is one. So you never see just an O floating around. All of the oxygen that would be reacted in a combustion reaction is an O2 gas. So you don't see a single oxygen atom by itself, because if there's two, they pair up, they form a nice double bonded molecule, and they go about their business. So, good old Hofsprinkle. So H2, O2, F2, Br2, I2, N2, and Cl2. These are all the diatomic elements. Yes, you are expected to know them. There are a whole bunch of different ways to memorize this. I'm a simple person. I just go Hofsprinkle, and then I just got to try to remember to not forget the I, because it can kind of escape me sometimes. But other than that, I'm good. And so if you ever see a reaction with hydrogen gas or oxygen gas, well, it's going to be H2 and O2. Fluorine gas, F2. Bromine is usually, if I remember right, it's a liquid. So it's the liquid Br2. So liquid bromine, it's Br2. Or even a gas. Doesn't really matter anyway what phase these are. It could be liquid oxygen. Yeah, that exists. You can do that. In normal conditions, it's a gas. But if you mess with the pressure or the temperature, you get it really cold, it'll liquefy. Nitrogen. Maybe you've seen demos with liquid nitrogen before. You can freeze something like a tennis ball and then it shatters. So it's a very cold liquid. And then Cl2, good old chlorine gas. So if you just see any of these elements called out, just recognize that they're not going to be just a Cl by themselves. It's not going to be an N by itself. They're going to be Cl2, N2. And it's going to affect what we talk about more in the next section. But just an early heads up on that. So, we have all our chemical formulas for the stuff we start with. We have all our chemical formulas for the stuff we end with. The reaction happens in the middle. What else is there to say about this? So we're going to talk in more detail about how we write these chemical equations in the next video. So right now we're just kind of introducing all the pieces. And so really the last thing to talk about is there's some stuff we can play around with the reaction arrow. So if you see, well, so if we heat the reaction, we put it like that. We say what we do, and then I'll talk about how we write it. So if we heat the reaction, then we put a Greek delta, which some simple people might think that's called a triangle. No, no, no. That's a Greek delta. Capital delta. That's a capital delta. We put that over the reaction arrow. So if you see that, you go like, oh, so like, maybe we put these together and then we added heat and we got something. Okay? In this case, no, this is going to produce a bunch of heat. We don't have to add heat. We don't have to keep heating the reaction. We don't have to hold it at a temperature for the one I've shown. But this is pretty common. So just like it's pretty common to have things dissolved in water, it's also pretty common to have to heat reactions up to make stuff happen. If a catalyst is used, then we also write the catalyst over the arrow. So it is listed over the arrow. Or, sometimes, if you've got like a delta that's already taken up real estate, sure, you can write it below. It's not too specific, honestly. So, for example, we can have a reaction like C2H4 plus H2. These are all gases, by the way. We can have this reaction happen, and we make C2H6. So we just put it all together. We put a few more hydrogens on our carbons. And that's also a gas. So we take ethene gas, we make ethane gas, don't worry about that. But excuse me, but we don't have H by itself, right? It's a diatomic, so we see H2. Now this reaction can be sped up considerably by putting platinum metal in there. And so to show that, this is what we do. So a catalyst doesn't get used up in the reaction. Reactants get used up. It doesn't get produced by the reaction. Products get produced. It's just there. And so what it does is, this reaction is going at a certain speed, and then this thing gets put in and it takes off. So it's like, the reaction's going along, and then it's like, oh, yellow light, so it punches it, all right? It just goes as fast as it can, because no one's going to stop for a yellow light, right? That's too dangerous. The person behind you is not stopping, right? So that's what this is. It's like, oh, yellow light, and so the reaction takes off, boom, and it goes even faster. So there is a rate of how a reaction progresses. And so we can use sometimes metals or acids or bases. There are ways to catalyze reactions to speed them up. And so chemists aren't just lazy, we are also impatient. So we generally are trying to speed reactions up, not usually trying to slow them down. And then also catalytic converters in cars for emission systems. The metal that's in those is actually platinum. So platinum is a very common catalyst. And we're not going to talk about why right now. There's a whole bunch of other stuff we have to talk about first. But if we get to kinetics in this class, I'd have to look at the syllabus. I don't remember. I think we do. Then I'll talk about it some more. And also, that's why sometimes people will go around and they cut out catalytic converters from cars because platinum metal is worth a pretty penny. And so if you see like a big old Escalade is going to have a big old catalytic converter. It's going to have a big old chunk of platinum in it. And so there are issues sometimes where people go to start their cars and they sound a little different because someone's cut out a chunk of the muffler to make off with their catalytic converter. Take it to the scrapyard. What else? Oh yeah. Sometimes you put stuff together and nothing happens. Then you just go NR. And you put it in the place of the products. And that means no reaction. Yeah. It just, nothing happens. Sometimes you don't get a reaction. Okay. And so, how do you know you have a reaction or not, right? Like, how do you know to put an NR there? Well, there's a couple indicators. So, a reaction takes place if there's like a big color change, a gas gets released, you measure a temperature change, maybe it gets hotter, maybe it gets colder. Both of those are on the table for possibilities. Sometimes you can get what's called a precipitation reaction. You pour two liquids together and then a solid forms. That's a good indicator that a reaction has happened because two liquids, you didn't change their temperature or anything, but a solid has formed. That generally means that a reaction has taken place. Or you can use some really high-end chemical analysis, spectroscopic tools, stuff like that to measure with light if a reaction is happening. Because just like atoms have those fingerprints, they have those absorption spectrums, molecules actually have that as well. And so if you see your absorption spectrum is changing, then there's a good chance that a reaction is happening. So, but if you don't get any of that, you just go NR. So, you're like, oh, I put carbon and oxygen together, nothing happened, NR. But in general, if you just have a piece of carbon sitting there, this reaction is going to go so slowly you might as well say no reaction. But you light that sucker up, boom, it takes off, yellow light, boom, and then you have a fire and you're making CO2. All right, so we are going to talk about how to write these chemical equations from scratch. So what I've done so far is I've just given you an example. I've explained all the pieces in it. Stuff we start with, stuff we end with. How do we know what separates them? Well, we put an arrow in there, and so we know this is beginning, this is the end. It's nice and kind of chronological from beginning to end. It points. And it's just like we read left to right. We've got our phases of matter. We've got a few details we can throw in. And these diatomic elements are going to be really key in the next section because we're going to talk about how conservation of mass applies these chemical equations. We're not going to make stuff magically appear or disappear, so everything we start for needs to be accounted for in the end. So that's called balancing a chemical equation. Now, everything I've shown you so far has actually been balanced. It just has been effortless. We're going to have to start showing some examples that require a little bit more effort in that direction. And that's what we're going to do next.